Okay.
Welcome, everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College London, and this is the new episode of the podcast Turbulence at the Exascale. If you're not familiar with the podcast, we are trying to gather the view of the community regarding exascale computing for turbulent flow, and we are trying to identify challenges and opportunity that will come with the new generation of supercomputers. So this podcast is a joint initiative from the UK Turbulence Consortium and the ExCALIBUR project, which is a 5-year project in the UK led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation. And its aim is to deliver research and innovative algorithm developments to harness the power of exascale computing in the UK. So today I'm very pleased to have Gary Coleman from NASA Langley Research Center as our guest. If you don't know Gary, Gary was professor in Southampton for quite some time, and he was leading the UK Turbulence Consortium a few years ago. So it's great to have him on this podcast today. So good morning, Gary.
Good morning. Thank you. Good afternoon to you.
So of course, Gary has a lot of research interest in high performance computing and in simulation of turbulent flows. So it's going to be nice to hear from him about what he's doing and where his research activities are going with respect to exascale computing. So first of all, Gary, for those who may not know you, please can you tell us more a bit about yourself, where you're from, what you have studied, and where and how did you end up working for NASA?
Okay, thank you. Sure. I was born in the States, in Missouri, and went to high school in Illinois and university at Southern Illinois. And then after a couple of years at McDonnell Douglas in St. Louis, I went to Stanford for postgraduate studies, and then had a few research posts with NASA Ames and then at UCLA. And then I moved to Southampton, as you mentioned, just before the 2000 year began, the new millennium, and stayed there until 2012. And I've been at Langley since then.
Great, fantastic. So may I ask you, how did you become interested in high performance computing and turbulent flows during your studies?
Sure. I worked with Joel Furziger and Philippe Spilart when I was at Stanford, NASA Ames, and got interested in that through them. We did a DNS study, a series of DNSs of an idealized planetary boundary layer for my thesis, and that's where I got introduced to the topic with all the colleagues at Ames, and especially through Joel and Philippe.
Great, thank you. And so you have been working for NASA for nearly 10 years, possibly. And what's the best thing about your current position, and how does it compare with the professor position in Southampton?
Well, the best thing about it is the kind of problems we get to work on. It's a nice combination of relevance and rigor. We're doing meaningful things with the proper tools, so we can get deep enough to feel like we've got a reasonable answer, but also looking at relevant things. And I've really been impressed and helped by the skill and helpfulness of my colleagues here. They've pulled me out lots of messes and helped me, pointed me in the right direction many times, and it's a really good situation. I don't have as much administrative work as I did in Southampton, which I don't mind, but I do miss teaching and interaction with undergraduate students. It was really helpful to have to think about explaining the fundamentals to a new group of students regularly, and I think that does help one's research to think about things in basic terms. But like anything, there's trade-offs with good and bad, but I'm grateful for especially the colleagues and the kind of problems I can study here.
Great, thank you very much. And so can you tell us, I know there's a lot of confidentiality issues possibly, but can you tell us a little bit more about the research project you are working on at the moment at NASA?
Yeah, I'm doing pretty fundamental things, so it's all in the open literature. We're doing a series of DNS studies, looking at separation in particular, smooth body separation. It's forced by adverse pressure gradients, and then trying to use that as databases for modeling. I've also been doing some studies of wall-bounded high-speed turbulence, looking at the effect of thermal boundary conditions on different quantities of interest for turbulence modeling in particular. And we've also gotten involved with trying to do some rudimentary studies of using machine learning to test and develop, if possible, RANS models. It's quite challenging, and we haven't had a huge amount of success yet, but we're plugging away. In fact, perhaps I can mention that this time next year, we're aiming to have a workshop here in Hampton Roads. It correlates with one of Philippe Spillart's birthdays, but the topic is machine learning for RANS modeling. And so any of the listeners and yourself and your colleagues who'd like to participate in that, please contact me for further details. There's also a link on Chris Rumsey's Turbulence Modeling Resource website where you can find the details about what that's going to be. It'll be quite useful, I hope. We're going to try and assess the state of RANS modeling and how machine learning has contributed to it. And we've got some experts coming and would value even more participation.
Oh, great. That's good to hear that there will be a workshop on this topic. May I ask you if you will touch also on large dissimulation modeling, because there is a lot of ongoing activities on this topic as well, or it will focus only on RANS modeling?
No, there'll be some machine learning for subgrid scale development. It's mostly for RANS because we're trying to see if RANS can be rescued, so to speak. But there is some overlap with LES schemes as well. Great,
fantastic. So you're doing a lot of fundamental research based on direct numerical simulation. So I think would it be possible for you to tell us a little bit more about what numerical methods you are using? So what type of flow solvers you are using and what type of parallelization strategy you are using?
Yeah. I've got two main tools these days. One is a spectral code that I've been using for many years. It was developed at NASA Ames back in the 80s, and it's been data parallelized with MPI. The algorithm was developed by Spillart, and as I said, back at Ames in the 80s, but it was parallelized when I was in the UK actually, and I greatly benefited from the UKTC and EPSRC's support of some work that David Scott did at Edinburgh to get this code into shape. So even now I'm benefiting from it. So it's quite an old-fashioned strategy, discretization, but it's still working well for the kind of problems we're applying it to, especially developing boundary layers subjected to pressure gradients for the incompressible case. The other thing I'm pushing pretty heavily on is also can be attributed to UK efforts is the Open SBLI framework that Neil Sandham's group has developed. I'm collaborating right now with David Lusher quite heavily, and we're doing a study of wall-bounded turbulence compressible flows. And that's been really useful, and I've been able to make some good progress now because of the whole strategy about it, how it's set up. I might say a few things about that in a minute, if I may. The last main tool we're using is a Langley CFD suite called Fun3D. It's got some adjoint capability, and that's been really helpful for our RANS studies looking at machine learning and collaborating with a couple of folks here. So those three things, a spectral code looking at incompressible wall-bounded turbulence, or boundary layer turbulence, and then compressible wall-bounded turbulence, and then the general CFD package. Those are my main tools these days.
Great. Thank you very much. That's very helpful. And so my next question is more related on exascale computing. And it's like, for your research group, would you say that when the next generation of supercomputers, exascale computers, will become available very soon, I guess very, very soon in the US, do you think that you can say that you're ready for this next generation of computer, or do you think, well, you said that the spectral code might not be up to date, but would you say that you're ready for exascale computing?
That's a good question. Time will tell, of course. I'm a little more optimistic than I may have been in the past because of my experience with this Open SBLI framework and this strategy about writing one source code in symbolic terms, and then using the Oxford Parallel Suite and the tools that the Southampton group have developed to generate executables for lots of different machines to do production, and I've really benefited from the ability to run on the GPUs that we have access to here. And I think I sort of stole a march, as they say, because I was able to take advantage of some of those GPU resources. Because of those strategies, I think I'm not as concerned as I said would have been probably a few years ago. But I think those kind of approaches are going to be really important for taking advantage of the big machines that are coming along. But so far so good. But nobody knows for sure, of course. I'm sure there'll be surprises and things we'll have to adapt to.
I agree with that. And let's say if tomorrow you have access to a very large exascale computer, my next question is what you are planning to do that you cannot do at the moment? I mean, is it just a matter of increasing the Reynolds number, increasing the resolutions, or you are planning to do, I don't know, add more complexity to the flow, looking at more complicated problems? What do you think you will be doing with an exascale computing?
Well, there'll certainly be a step forward in complexity, I think, but it'll probably be mostly in parameter space. It'll allow us to do deeper and more meaningful parameter studies, case studies, to look at different schemes, and therefore it'll increase the value of the work, I think. And also, it sounds kind of tedious, but I think a lot of the current DNS results have suffered from the fact that the statistics aren't quite as resolved as we'd like them to be. You push as far as you can and you burn as much resource as you have access to, but some of the profiles aren't quite as smooth as we'd like them to be. It's interesting. I used to, when I first studied started in the field, I was keen for all my papers to have a picture of all the unsteadiness and the jaggedness of the flow field to show that we were capturing all the scales. But now I'm more excited by smooth profiles that come from the statistics that show that we've run them long enough to get meaningful things. So again, I don't really know for sure, but I'm planning to hopefully do a series of case studies that will increase the value of the studies that we've done in the past, and also hopefully be able to spend even more time tightening up the certainty surrounding the statistics, especially higher order quantities. As you know, get kind of uncertain unless you really nail them and run them for long periods of time.
Great, thank you very much. And of course, you have a lot of experience in CFD, and you're familiar with the CFD community in the US and in the UK. And so my next question is, do you think that overall the turbulence community is ready to harness the power of exascale computing, or do you think there is a long way forward?
Well, I think we're keen to try. We're always chomping at the bit to get access to more resources. I'm always having to ask to top up my allocation to use it. I think the fact that we're keen to try and do things will give us some energy to step forward. I don't know, of course, if we're going to hit any insurmountable bottlenecks and about the resources and things. But as I said before, one thing that's going to be really useful is a strategy like OpenSPLI, where you don't have to rewrite your source code every time the machine changes. And because of that, combined with our natural eagerness to branch out into more complicated, challenging problems, I think we'll use what they give us in one way or another.
And then, so you are following this domain-specific language strategy with OpenSPLI. Is there any plan to do similar strategies with other NASA codes, or this is just what's the plan on NASA overall? If you can comment on that.
Well, I would if I could, but there's quite a lot of diversity. A lot of my colleagues are involved in more computer science type things than I am. I'm just basically an engineer trying to use these DNS codes as tools to study physics and improve turbulence models. So I'm concerned long enough to get the tools to work, and then I kind of go and push in terms of the physics and the modeling. The hints I get from my colleagues, there's a lot of different branches that I'm not intimately familiar with, but the colleagues I talk to on the way to lunch and so on, I think they're up to speed, and they're working with the DOE centers quite closely to try and take advantage of the resources there. I've got a couple colleagues who are blasting away on these national allocations, and so I think I've drifted away from answering your question, but hopefully there's some response in there to what you're asking about.
No, that's good to hear.
Okay, I'll stop.
Good, and I have a couple more questions. It's a more my next question is more about the hardware. I mean, you might not be, as you said, a full expert in hardware, but if there is one thing that you can change about hardware in high performance computing, what would that be?
Well, it'd be nice to do something to speed up the data transfer and ease the storage restrictions. There's a huge amount of data flying around these days, and it gets pretty tedious having to. Even now, a good fraction of my production runs in DNS are just spent writing the restart file at the end, and I can see how that's going to be an issue that's going to require careful attention in the future. That's probably the main thing I'd like to change. Besides having access to more of the resources, I'd like to. It'd be nice if they could address these questions about the volumes of data and how to transfer it and store it. Great,
thank you. And my last question is: we are talking a lot about exascale computing, and I would like to know if you have any views on what do you think will come next, and in particular, do you think we are going to still see an incremental change? So GPUs, CPUs that are faster and low energy consumptions, or do you think we are going to see in the next maybe 10, 20 years a complete revolution in terms of hardware? Where do you think we are heading?
I have no idea. I don't trust my forecasting skills enough to say anything meaningful. I know there's quite a bit of activity on this quantum computing approach. It seems like there's some severe bottlenecks there. I don't know. Like I said before, they've been forecasting the demise of spectral codes for years, and I'm still using them. Found it should solve reasonable problems. So a lot of things that I'd expect to happen haven't happened, and vice versa. I do guess that, like you said, the energy consumption is going to be a big issue in the future, which I suppose will point us more in the direction of GPUs. But I don't know. I don't know. I should probably just leave it there. But again, I can underline that point about how the usefulness of having the strategy about not making the research scientists do the coding every time the machine changes. That's going to be a big part of anything that goes forward.
Yes, that's probably a good thing not to say too much on this, because we don't really know what's going to happen. Anyway, well, thank you very much, Gary. It was nice to catch up with you and to catch up with your research. And I will when I will post the podcast, I will make sure to add the link to your to the workshop that you are organizing next year. I think that will be a lot of people are going to be interested in this. So thank you very much. Thank you very much for your time and for talking to us. And for everyone, we wish you all the best, and hopefully we will see you soon in a new episode of this podcast. Bye-bye.
Okay, thanks very much. Thank you. I got to say, I appreciate seeing UKTC in such good hands. It's nice to see it flourishing. So thank you for that.